Truly excited to be back again, actually talk with you all about a particular topic that's kind of a continuation from our Organic Chemistry 3 series. And in here we're going to be looking at electron counting that helps to actually explain the stability of metal complexes. Like in our previous videos, we talked about various metals, mainly in the transition area in the periodic table, and we actually noticed that anytime there is a coordination with any ligand, they usually obey the, I would say, the 18 electron principle, and this actually shows the stability of a particular metal complex. Now we're going to see how we're going to introduce this particular key note into various of metal complexes, like for example palladium and iron, and we're going to see variations of examples in here. Like first, looking at this particular example where we're looking at palladium actually reacting with a phosphorus phenide ligand, and this interaction in here is quite interesting, and we're going to dive more into not only the overall, I would say, electron count, but also how the charge actually determines how many electrons are in that particular main metal, which is palladium. Now in this particular part we see that I would say a tetra-case triphenylphosphine ligand in here has, I would say, when it is in its ordinary form, has a lone pair of electron, which is kind of similar to what we notice from its neighboring atom, which is nitrogen, phosphorus and nitrogen. So seeing this in their neutral state, when it coordinates with this particular metal, which is palladium, what happens now is that the lone pair is actually donating, or is being donated into this particular free space of palladium, and what that results in is that this shows the electron pull towards palladium, and what that results now in is, okay, since the overall charge is actually 0, what is the charge on palladium? So since we notice that in terms of the charge, we don't know what the charge of palladium is, but we know that the ligands here, or I would say the charge when they are in their natural state, is actually equal to 0. Then we have 4 of those ligands. 4 times 0 equals 0, and that shows that palladium has a 0 charge. And in this particular case, what we can infer is that palladium has 10 electrons if you look at it in the periodic table. And in this particular case, what we can now result in is that, okay, since palladium has 10 electrons, the 4 ligands are actually donating 2 electrons each, and that plus the palladium total number of electrons, which is equals to 10, gives us a total of 18 electrons. So that being said, the number of electrons in this particular metal complex is equals to 18. Now this shows that this particular complex here is a stable complex, and once it's stable, it's actually noticed to be so much more stable that it actually will actually lose a ligand, or one of the ligand, to actually be involved in any reaction. So that's about it for this particular first part. And the second one in here is looking at iron actually coordinating with a cyclopentylene ligand, and what we notice here is that this particular ligand actually comes from this particular compound, where it's actually equivalent to a negative charge on one of the carbon, and we have 2 double bonds on either side of the 2 carbons. And what that implies now is that the charge on this particular ligand here is -1, and that means that we have -1 on both ligands, and also we notice that from our counting of how many of those electrons are actually donated into this particular metal here, we notice that from our ether, I will say 5, because 5 represents the number of atoms present in that particular ligand. All atoms contribute their electrons to the metal. So what that means is that we have 6 electrons donated into this particular metal. So that being said, what is happening now to this metal, and how many electrons, or what is the charge on this metal? So first off, looking at the charge, we actually notice that since we have 2 ligands that are actually both -1 in here, and we don't know what ion's charge is, but the overall charge here equals to 0, we realize that iron is actually a +2 in terms of the charge. So once it is a +2, what that implies is that if we count the overall, I would say, number of electrons, for this to be stable, it must be equals to 18. And what that means now is that since we have 6 electrons being donated each from the ligand, so times 2 of the 6 electrons in there, and how much iron has, that needs to be determined. What that means is that 18 minus 12 gives us 6. So what that implies now is that iron actually contains 6 electrons, specifically iron 2+, and this iron 2+ is actually in the d orbitals, and once it actually accommodates 12 more electrons, then this particular complex is actually considered to be extremely stable. Now finally, here is going to be a tricky one, where we're going to look at palladium, but now it's coordinating with chlorine and this particular compound right here. So let's look at this compound right here. This compound actually comes from nitrogen, which has a lone pair, and this has a triple bond, and this triple bond is attached to a carbon, and the carbon here is attached to a methyl group. So the overall charge of this particular compound here is actually 0. So in this part, it has a 0 charge. So when you're looking at the charge distribution, we notice that chlorine actually comes from a negative charge chloride. So what that results in is that we have -1 in terms of the charge coming from each of the chlorines, and in here we have an overall charge of 0 and 0 right here. So what that now results in is that once we're trying to do the calculation for the overall charge for this particular compound, which is also considered to be 0, we now have to determine what the charge of palladium is. So to do that, what we do is that we sum all the charges, and then we find what palladium is. And in here we have 0 for the nitrogen, I would say, cyanide methyl group, and on the other side we have 2 -1 coming from the 2 chlorines. And what that results in, we figure out that our palladium here is a +2 in terms of the charge. So what that implies is that palladium actually loses 2 electrons, therefore it's going from 10 electrons down to 8 electrons. So that being said, once we know that it has 8, to find the overall electron count, what we now do is we add 8 coming from palladium plus 2 electrons coming from both the chloride and that of the cyanide methyl compound, and what that results in is 2 electrons times how many of them? 1 2 3 4 and what that results in is that 8 plus 8 gives us 16 electrons. So now we notice that this has 16 electrons. It doesn't obey the 18 electron rule. So since this doesn't obey the 18 electron rule, this implies that this complex doesn't fulfill the 18 electron rule. However, still stable, but this is very, very reactive. So that being said, we have been able to actually differentiate and see the consequences between the stability and also the reactivity of a particular metal complex to the electron count, which is also based on the charge of each of these ligands right there. And this is applicable to all compounds or metal complexes. All the same, thanks for following me through this, truly appreciate it. Hit a comment down below, let me hear your thoughts about this. By that way, I can talk to you all later. Stay smart and believe in yourselves.